In this video we're going to look at using the cosine rule to find missing lengths and angles in non-right angle triangles. We saw that the cosine rule could be used to find a missing length when we had two known sides and an enclosed angle. So for example, if we looked at this one, we could use the cosine rule to find the length uv. We also saw that we could find a missing angle if we had three known sides. So if we look at this one right here, we could use the cosine rule to find any of these missing angles. In the video we're going to work through some basic examples. We'll then look at the proof, and in later videos we'll combine the sine rule, the cosine rule and our trig ratios to solve problems in context. So let's start off by looking at finding a missing length. So we're looking at missing lengths in non-right angle triangles, or at least triangles where we can't find a perpendicular height. So missing lengths. What I'm going to do is go ahead and draw up a triangle. So we'll have some scalene triangle, and the triangle will look something like that. So let's say it looks something like so. I'm going to have the angle here, and this is going to be now the angle, putting this on as A. So I'm going to label that capital A, this is going to be little a. This is going to be B, and this is going to be C. In the formula book, we're given the cosine rule is A squared is equal to B squared plus C squared minus 2BC cos A. So this is given to you in the formula book. Okay, so let's go ahead and look at this in action. What I'm going to do is just sketch up a triangle. We'll put some dimensions on and go ahead and find now the length of an unknown side. So let's say we've got something that looks a bit like this. Let's open that up and we'll do that. So what I'm going to have is some angle here. Let's say this angle is going to be 147 degrees. So we've got 147 degrees. This side I'll have now, let's go for 8.4. So let's have 8.4 here. And let's say this one is going to be 8.9. So what we want to do is find this missing length. So we have two known sides and the enclosed angle, which is required. So what I'm going to do, I'm going to label this angle as A, so that's big A. We want to find now little a, which is the length from here to here. I'm going to call the 8.4 now, this is going to be B, and the 8.9 is going to be C. We can of course call these ones B and C the other way around. So what I'm going to say then, it's A squared, the length I'm looking for, is going to be B squared, which is 8.4 squared, plus C squared, which is the 8.9 squared, minus two lots of B, which is going to be the 8.4, multiplied now by C, which is the 8.9, multiplied by the cosine of the angle, which is 147 degrees. So if we put the calculator in degrees mode, shift mode 3, we can go ahead and find that length. So I'm going to say now that this is going to be the square root. I'm going to take the square root of both sides of 8.4 squared. So 8.4 squared plus 8.9 squared. And then we're going to have now minus two lots. So 2 times by the 8.4. So times by the 8.4 times by the 8.9 times by the cosine now of 147 degrees. Just closing that off, we can go ahead and find that, and that is going to give me 16.588 and so on and so forth. So I'll say that this is going to be 16.6 units, and that is given now to 1 dp. So 1 dp, I've rounded that off. So all I've done is simply use this. In an exam, you might want to write out the steps here to give a value for A squared. I've simply taken the square root of both sides. An interesting result here now is when we've got the cos of A equal to 90 degrees, the cos of 90 degrees is 0, and it gives us Pythagoras. A squared is equal to B squared plus C squared when we have a 90-degree right angle. Okay, let's now look at missing angles. So if we put this on, we can look at finding missing angles. In terms of using the cosine rule, we can use it in this particular form, or we can rearrange it. If you want, you can just leave it like so, or you can write now that cos A is equal to B squared plus C squared minus A squared over 2BC. So the cosine rule for finding an angle can be rearranged to give that. What I've done here is added 2bc cos a to both sides, subtracted a squared and divided by 2bc. You might just want to work with this and solve it as you go. I personally like this particular approach, but it's not essential. So let's go ahead and draw a triangle. We will have now, let's go ahead and do this, and we'll have on something that looks like this. So this is not massively accurate, but it will give us some idea now of what we want to do. So let's say that this is going to be, let's say that one is going to be 9, let's say that that one is going to be 7, and this one is going to be 11. So in this particular case, we would use the cosine rule as we have to find an angle given 3 lengths. So let's choose an angle to do, and we'll take this one. Often I like to work with it with this configuration. So what I'm going to say is that this is going to be angle A, this is going to be A, this one is going to be B, and this one is going to be C. So I can write now that cos A will be equal to B squared, well that's 9 squared, plus C squared, which is 7 squared, minus A squared, which is 11 squared, all over now 2 lots of B times by C. So 2 times by 9 times by 7. So what I'm going to do is get a value for cosine of the angle, so cosine A. So we've got 9 squared, we've got 7 squared, we're going to subtract from that 11 squared, we're going to divide that, and again you can write this however you want, you can use brackets or you can use a multiplication as it did on the last one. So we can see that cos A is 1 over 14. That is the cosine of the angle. It's not the angle, so as we've seen before, we need to take the inverse cosine of both sides. So the inverse cos, or cos to the minus 1, or arc cos of 1/4. So 1/14 I should write. Let's put 1/14. I think that's what it said on the calculator. There we go. And check your in degrees mode. Shift cos, the inverse cosine of that answer, and that's going to give me 85.9. So 85.9 degrees. So the angle A is 85.9 degrees, and that's given to 1 dp. So nice and straightforward, we're simply using that. Now if you'd gone this way, you could have just subbed them in here. You could have just put them in. So what we would have had is 11 squared is equal to 9 squared plus 7 squared minus 2 lots of B, which is 9, multiplied by C, which is 7, multiplied by cos A. So all you'd need to do is rearrange that and solve if you used this particular formula. I prefer to use this one, but it's entirely up to you. Okay, let's go ahead and answer some basic questions. In later videos we will look at these in context and when we combine them with the sign and other trig ratios, but for now we'll just do some straightforward ones. So for each of the following triangles, find the unknown angles and sides. So let's start with this one right here. So what I'm going to do is just draw on this. So what we're going to have is something that looks like that. So we've got now the 2 known sides and the enclosed angle. We'll also see that the cosine of 60 degrees later in our work gives us a nice value of 1/2. But for now, all I'll do is plug this into the calculator. So to find A using the cosine rule, we can say that A squared is equal to B squared plus C squared minus 2BC cos A. It doesn't matter which one of these I call now B and C, as I'm not introducing these angles. So I say that that one is going to be B, that one is going to be C. So I'm going to say that A will be equal to the square root now of B squared. Well, that's going to be 3.5 squared plus C squared, which is going to be 3 squared, minus 2 lots of B, which is 3.5, multiplied now by C, which is 3, multiplied by the cosine of 60 degrees. So if we go ahead and do that in the calculator, again you might want to write out this numeric value before you give your answer. 3.5 squared plus 3 squared. So check what, don't want to do that, there we go. Check what the mark scheme is worth and check what your examining board require. Some might need you to show A squared is equal to some value to gain method marks. So times by the cosine, hopefully this is in all right. Cosine is 60 degrees, so let's just check that. So 3.5 squared plus 3 squared, 2 times 3.5 times 3 times the cos of 60 degrees, and that will give us now the square root of 43 over 2, which is going to give us 3.27. So 3.278, so we'll say 3.28. So if we think about this reasonably, is that a logical answer? Well, this is almost almost an equilateral triangle, not massively, but if you look at it, it's fairly close. If we've got a 60-degree angle here, 3 and 3.5, it's not going to be a massive distance off. This one just here, we will leave this one, but if you wanted to do this one, if we think now what we've got is for two sides and the enclosed angle, so we would simply label this up and substitute in. So we would say that this now is the angle A, this is going to be A, this is going to be B, and this is going to be C. Plug in all of those values in, you will find that length right there. So let's go ahead and find these. Now, we're asked to find all the unknown angles. So with this one, let's just go ahead and do that. Let's just start with 1. Once we've got 2, we've got 3. Hopefully that should make sense. If you know 2 of the angles in a triangle, you know the third as they sum to 180. So let's go ahead and call this one A. We'll find that one first, and we'll say that this is little a, and then we'll say that this one is going to be B, and this one is going to be C. So we can say now, and I'll write it out in full, A squared is going to be equal to, oh, in fact we'll go for, no, we'll do it this way first. We'll say that A squared is equal to B squared plus C squared minus 2BC cos A, or we could say that cos A, so cos A is equal to B squared plus C squared minus A squared all over 2BC. I much prefer this. I think it's a lot easier to work with. So what we can say using the bottom one now is the following. We can say that cos A will be equal to B squared, which is 2.1 squared, plus now the 3.2 squared, minus the 4.3 squared, divided now by 2 lots of B, which is 2.1, multiplied by C, which is 3.2. So if we get a value for that, let's put that in. So we want 2.1 squared. So 2.1 squared plus now the 3.2 squared, so let's put 3.2 squared in, minus the 4.3 squared, and we need to divide that now by 2, and again you can use brackets if you want. If you want to put brackets in, you can do brackets, 3.2. So that's going to give me the value of cos A, which is negative 2/7. So we can say that cos A is going to be negative 2/7. So we need to find A. We take the inverse cosine of both sides of that equation. Cos to the negative 1 of negative 2/7, and we'll get a value for that. So if we do that, let's go ahead and do that one. So we'll take now the inverse cosine. So inverse cosine now of negative 2/7, and that is going to give me now 106 degrees. So 106 degrees is our answer. And if you look at that, not a massively accurate drawing, 106.6, so if you wanted to write it to one decimal place, 106.6. So let's write that in. So A is going to be equal to 106.6 degrees. And again, you could have just substituted it in the other way. I've taken it now B squared plus the C squared minus the A squared over 2BC. And that's the calculation now. If we just look back, we've got now 2.1 squared plus, let's grab that up, plus the 3.2 squared, and then we minus in the 4.3 squared over 2 lots of 3.2 times by 2.1 or the other way around, and we'll work from there. So if we wanted to go ahead now and find another one from here, we could apply that, or we could go ahead and use the sine rule. Given that we've now got one angle and 2 known sides, we could do that, or we could use a second application of the cosine rule. I personally use a second application of the cosine rule just in case my answer was wrong. So with this one, now if we wanted to set this up, let's go ahead and put this on. We could say that this was going to be A, this was going to be B, this was going to be C, and then we could go ahead and find this angle A. We could find the other ones from there by simply using the cosine rule. So there we go, basic applications to find missing lengths and angles in non-right angle triangles. Okay, let's move on and look at this cosine rule, and to finish off with, we may as well do the proof that it does work. Let's grab a fresh page and then I'll do a sketch. So what I'm going to do is just draw up a triangle, and we're going to see how this works. So what I'm going to have then is some triangle that looks like that and looks a bit like that. I'm going to now have some perpendicular height. So if I put a perpendicular height on, we can put that just there. what I'm going to do is label this angle right here. This is going to be now A, so let's put this on. Then let's just put A just here. We're going to have the angle B just here, and we're going to have the angle C just here. So if I just do that, that's going to be C, and this one is going to be B. So let's put B just here, and I'll just make that blocked off. There we go. So this is going to be A, we've seen that before. This is going to be B. This whole length right here, sorry, this is going to be C. Let's put C on rather than B. This whole length right here down the bottom is going to be B. But what I'm going to do is split this up. I'm going to split this into two right angle triangles, and I'm going to say that this length now from the point here to the point here is going to be X, and then this is going to be B minus X, such now that this total distance is just B. I'm going to call this one H. So if we think about this reasonably, what we can say is, using Pythagoras Theorem, we can say that H squared, just looking at this triangle here, H squared is going to be C squared minus X squared. So taking now, and I'll call this the blue triangle, let's just call this the blue one, so that's the blue one, and then we'll have the red one. So two little right angle triangles as I've got a perpendicular. So if we look now at the blue triangle, what we're going to do is state now that H, using Pythagoras, so H squared will be equal now to C squared minus X squared. If we now take the red triangle, we can say that H squared is going to be equal now to, and just look what we've got. We've got here A squared, and then we're going to have minus the quantity B minus X all squared. So if we look at that just here, that makes sense. This one squared plus this one squared is equal to that one squared, or H squared is A squared minus now the quantity B minus X all squared. If H squared is equal to C squared minus X squared, and H squared is equal to A squared minus X squared, we can say now that H squared minus X squared will be equal to A squared minus B minus X all squared. And if we expand that out, that will give us B squared minus bx, which is minus 2bx, and then we'll have plus x squared. So just tidying this up, we've got c squared minus x squared is equal to a squared minus b squared. Then we're going to have plus 2bx, and then we're going to have minus x squared. We can see that these x squareds are going to cancel, and I can write this now as c squared is equal to a squared minus b squared, and then we're going to have now plus 2bx. This isn't looking too dissimilar to a squared is equal to b squared plus c squared minus 2bc cos a. So I'm just going to do a bit of rearranging. I'm going to add b squared to both sides and subtract 2bx. So what we're going to have on the right hand side is a squared. On now the left hand side we're going to have b squared plus c squared minus 2bx. So the only thing that's different now to this and the cosine rule is that we have x here and we have c cos a here. But if we go back to the blue triangle, let's just use our basic trig ratios, and I'm just going to sketch them up. So remember from before when we had our trig ratios, and I'll just put this on, we had our division line just here, and when we were dealing now with the cosine, we could say that c, so c, a and h. So if I wanted now the adjacent here, what I could do is write that in terms of the hypotenuse and the cosine. So what we can say is that that length x is going to be now, so if I want to know the adjacent, it's going to be the cosine of the angle multiplied by h. So in this particular case, we're going to have c cos a. So don't get this one confused here with c and c, this is just the cosine. What I can say is that x is equal to c cos a. This length right here is now the cosine of the angle, which is cos a, multiplied by the hypotenuse. So therefore what we can write now in here is that b squared plus c squared minus 2b, and then instead of x, c cos a is going to be equal to a squared, and that gives us now the proof of the cosine rule. So all I've done is a little sketch here, and hopefully that's made some sense. I doubt you'll be asked to prove it, but I think it's interesting nonetheless. So there we go, that's a cosine rule for finding missing lengths and angles in non-right angle triangles. And in later videos we're going to look at some functional questions, and we're going to apply both the cosine rule and sine rule in tandem.